So let's talk about determining what intermolecular forces might exist between two molecules from the chemical formula. So to start with, one thing we want to make sure we understand is that intermolecular forces are really about molecular compounds, and you can kind of tell that from the M, right? Well, what that means is that we're only talking about elements that are molecules that are covalently bonded together. So that might be a first step, is make sure it's not a trick question and it's an ionic compound. So these are covalent compounds or molecular compounds. Now, we know, just to review, we know how to tell an ionic compound by you're going to have at least two elements next to each other, right? And one is going to be typically a metal and the other is a non-metal. So a metal plus a non-metal for our ionic. Right? And so, for example, sodium chloride. Sodium is in group 1, chlorine's a halogen, so we can tell we're dealing with a metal from a non-metal. Now, I say typically because we do have to recognize that many, probably all, now that I think about it, of our polyatomic ions are non-metals. So what about ammonium chloride? The reason I can tell this is an ionic compound is it's even though these are all non-metals, but I can tell because I'm familiar enough with my polyatomic ions that when I see NH4 in my brain, or CO3 or PO4 or any of those, when I see those, my brain can translate that into, oh, that's a positively charged cation. That's ammonium. That's NH4 plus. So I know then that I have a cation next to a nonmetal, which tends to be an anion. So in general, when I see that kind of formula, either a metal with a nonmetal or, and there are not a lot of positive polyatomic ions, but if I see a positive polyatomic ion with a nonmetal, that I also can translate that into ionic, and then I'm not talking about IMFs, because this is really talking about a type of bonding. This is an ionic bond, and so IMFs would not apply. So if I have a chemical formula, though, and I recognize it as a molecular compound, so for example, looking at like carbon dioxide, that's a metal, that's a non-metal and a non-metal, so I recognize that as being covalently bonded together. So then the question of like, okay, how do two different, so I know that the bonds between the carbon and the oxygen are covalent bonds, but what's the attraction between one CO2 and another CO2, one carbon dioxide molecule and another? And that's what these IMFs are about then, is they represent the attraction between one of these and something else. And a lot of times we're just talking about another CO2, for example. So step 1, make sure you're not dealing with ionic, because then IMF doesn't apply. And then make sure that we really know what are our intermolecular forces. What are the different kinds? So there's three kinds of these, these dots. Like that's the intermolecular attraction. So let's just kind of review. What are our three types of IMFs, and then how will we recognize them? So my favorite of all is the hydrogen bonding. It's the strongest, it's the coolest, it's all over the place. You see it in your life whether you realize it or not. You depend on it in your life whether you realize it or not, and it's a huge part of our biology. So not hydrogen bonded or hydrogen bondage, that's inappropriate. Hydrogen bonding. So that's one type. The other is dipole-dipole, sometimes called dipole-dipole interaction. And then last but not least, London dispersion. Now, if you're a little bit more biology bent, which is definitely okay, I have an undergraduate degree in biology, so I love my biologists. These two together are often given just a general term to count both of them together, van der Waals or van der Waal forces. Because chemists tend to go ahead and separate them out, but if you've taken biology or you plan to take a lot of biology, you'll become more familiar with this, where they talk about van der Waals and hydrogen bonding. Van der Waals is just separating these two out. So how are we going to just look at a chemical formula and determine which of these is really the predominant intermolecular attraction? And again, that's what this line is representing, how this is attracted to another one when they're mixed together. So this goes back to this really builds. One of the reasons I think is quite challenging is it really builds on past information, because you can tell from a chemical formula if something is ionic, but you actually cannot just tell directly from a chemical formula which of these exists, which is unfortunate. So that means there's really another step in the process, which is you have to determine its Lewis structure. This actually goes back to more the bonding, the molecular shape, VSEPR, polarity, electronegativity. So it builds on a lot of previous stuff. So the truth is, you can't determine the IMF directly from the formula unless you can translate that formula into knowing what the molecule really looks like. And that's one of the reasons we have to learn those steps before we can talk about intermolecular attractions. So you might recall when we did Lewis structures, you remember we determined, okay, we've got 4 valence electrons here, 6 valence electrons, but we have 2 of them, so we have to double that and total the number of valence electrons. When you go through all that process, if you correctly create the Lewis structure, you are going to get this. And we've learned this before, so I'm not going to go through all the steps, but you might want to go back and review if you're not really sure how to get from this to this. But that is really a critical part. We have to take a formula and we have to be able to figure out what's bonded to what and what does the molecule look like, because that is going to get us through determining which of these it is. So let's go through and decide what are the intermolecular forces between carbon dioxide molecules. So if we have a balloon filled with carbon dioxide, which is pretty easy, put a balloon over a bottle and put some vinegar and baking soda in it and it will generate carbon dioxide. How are those molecules in there attracted to each other? So right away we can exclude hydrogen bonding because there's no hydrogen, right? So we know we're not hydrogen bonding. Oh, I want to be a different color here. Let's do orange. Nope, purple. Sorry, the color is very important. So it's not hydrogen bonding. So we're left with dipole-dipole or London dispersion. And the truth is all molecules have London dispersion forces. It's just that for some molecules, that's all they have. So technically, we already know London dispersion forces exists in this molecule, because as soon as you have electrons that move around, you then have an opportunity to have an area randomly have a temporary uneven distribution of electrons. So we actually know this is a possibility. The question is, because dipole-dipole are stronger, if we have that, that's the one that makes the biggest difference. So dipole-dipole is for polar molecules. You can even hear it, dipole, 2 poles, polar molecules. So really what we're asking is carbon dioxide polar or not? And again, this is going to really make you look back on some previous content. Now, you might be thinking, well, I don't have my electronegativity chart and blah, blah, blah. That actually doesn't matter in this case because it's linear. This is a symmetrical linear molecule, meaning even if we got out our electronegativity chart and realized there's a dipole here, it is evened out or canceled out by the dipole over there. So carbon dioxide is a non-polar molecule. Well, that then would exclude this one, which means carbon dioxide's primary intermolecular force is London dispersion forces. So what that means is that these electrons in their random movement throughout the molecule, so here's think of the molecule as a whole thing, we get temporary, I always think of it as blinking lights. We get just a moment where a lot more of them are over here than normal, and that makes it a little bit negative, and then they move somewhere else. And it's really that temporary, momentary, and induced dipole that causes a very weak attraction between other carbon dioxide molecules. This helps us understand why carbon dioxide is a gas at room temperature, whereas water, which is actually a lighter overall molecule, so you'd expect it too to be a gas at room temperature, is not only a liquid at room temperature, but stays as a liquid for a very, very long time, all the way up to 100 degrees Celsius. And in fact, let's talk about that. Why? Water's so funny. Why is a molecule that's even lighter than this one a liquid for so much longer? So you probably know water's Lewis structure without even really having to think about it. A lot of students know it even before they ever take a chemistry class because they've just seen it. Water is an oxygen single bonded to 2 hydrogen, and then the oxygen has the lone pairs. So when we know it has London dispersion forces, and then we've learned that water is polar, right? The electronegativity difference is very great. It's not canceled out, and they even work together toward these lone pairs. So, but what we actually have is it's so polar. This electronegativity difference between oxygen and hydrogen is so strong that we've given this IMF its own name. Rather than say dipole-dipole, we have given this the attraction that it would feel with another one. It's not this bond. It's really actually, I should have said this. The attraction here, ignore that, is so strong. This dipole-dipole attraction is so strong that scientists were like, it needs its own name because it's almost its own thing entirely, even though it also results from polarity. And that is what hydrogen bonding is. And we're going to see hydrogen bonding when hydrogen is bound to the 3 most electronegative elements on the periodic table. So hydrogen to oxygen, hydrogen to nitrogen, and hydrogen to fluorine. Now, in some molecules, the hydrogen to sulfur bond is actually strong enough, but mostly that refers to hydrogen sulfide. So don't worry about that. That's just an interesting tidbit if you want a little bit extra research. So then for dipole-dipole, how will we know? Again, we'll have to go through that same thing. We'll have to go through all those steps that we are exploring right now. We'll have to, let me think of a good one. You know, one of the ones we looked at on one of the tests or quizzes was so imagine this was the question is here's the chemical formula. How can I tell? Now I have hydrogens, so maybe it's hydrogen bonding. So what we'd have to do, I'm not going to go through the whole process of developing its Lewis structure. But you know, you guys remember that you'd have to determine this many valence electrons plus this many, and we'd have to add it all up. We would eventually come up with the structure of what happens to be formaldehyde. Not that you would be expected to know that off the top of your head, but we would end up, so you can see here our hydrogen is not bound to an oxygen. It's bound to the carbon. So it's not hydrogen bonding even though we had hydrogens. That for hydrogen bonding, it has to be bound to, hydrogen has to be bound to what I say a NOF. NOF. It has to be nitrogen, oxygen, or fluorine. And again, there's some little exceptions, but we don't need to worry about that. So that leaves these other 2. Well, you know, again, I could look at an electronegativity chart, or you kind of start to realize, like, oh yeah, this is a polar bond right here. We have a little bit of polarity here. So it's not just London's dispersion forces. There's going to be an attraction to, let's see, let's put hydrogens there. Put our oxygen over here. The partial positive of this molecule will be attracted to this partial negative here, and so this is dipole-dipole. And so I have to use, to identify a dipole-dipole, I have to be able to use the skills I've learned in the past to take a chemical formula, turn it into a Lewis structure, and then use my knowledge of electronegativities in the periodic table. So common polar bonds. Carbon to oxygen, carbon to nitrogen, and that could be a double or a single bond here. Carbon to like fluorine or chlorine or any of the halogens. Those are really common, and you'll get to where you don't really need to think about it. One important thing I always like to point out for London dispersions is if it is a hydrocarbon. So what that means is that it only has hydrogen and it only has carbon in the formula. You shouldn't even have to figure out the Lewis structure. You just know non-polar.